All right. Could we settle down, please? I'll let you go early if you settle down. No, I'm just kidding. No. Okay, so let's go back to reviewing our basic calculus, and then we'll go over to trying to solve our first optimization problem, and then go to multivariable calculus. Okay, so far, let me just summarize the story that we have found. Actually, it's up there somewhere. Here we go. So that's the summary of the story that we were talking about last time, not last time, just a few minutes ago. So FR, if it stands for the rth derivative at the point x0, if you're talking about one-dimensional functions, the most general story that you want to do is that compute the first derivative, which is, it should have been not equal to 0. A first derivative which is not equal to 0. If n is even, then if it's a local min, if this derivative is positive, it's a local max otherwise. If the first derivative for which the derivative is not equal to 0 is odd, then it's neither a local min nor a local max. It's a point of inflection. And that's the counterexample that I was talking about before. The left-hand curve is, which I don't know. At least the first guys can see it. The back guys, I don't know. So the one on the left is y is equal to x cubed. The one on the right is y to the x fourth. And to differentiate these, you'll have to keep on taking derivatives until you get a derivative which is not 0. With polynomials, you're guaranteed that you will get a finite derivative which is not 0. With other kinds of functions, it's not clear. Okay. Now, really what we are interested is not really a local minimum. We are interested in something called a global minimum. And typically, in optimization problems, we are interested in the global minimum over a domain. We typically are not interested in the global minimum for x taking values from minus infinity to plus infinity, but taking values in some finite domain. Where does the domain come from? Domain comes from various operational restrictions. Typically, if you're trying to invest in some market, let's say if you're a mutual fund, you can't invest negative amounts. You can't short sell. So the decision x, the relevant domain over which this function is interesting to you is x non-negative. There might be margin restrictions and so on. So we're going to call a point x0 the global minimum over a domain if it is the minimum for all values in that domain. F of x0 is less than or equal to f of x for all x in the domain D. So if you look at the domain over here, which is from -2 to +4, there are two local minimum. Up here, there's a local minimum. It's a very shallow local minimum. If you go a little bit on both sides, that point x0 is actually the minimum point there. But there is only one global minimum, which is this point down here. This point is also a local minimum. That is also a local minimum, but only this is a global minimum. So the question is, how does one find global minimum? In optimization, we're not really concerned about local minimum. Fine, local minimums are good. The only reason we talk about local minimum is because they're easy to compute. You can take the derivative, check few conditions on the derivative, and you're done. The thing that I'm interested in is not the local minimum. I'm interested in the global minimum or the global optimum. If I'm trying to maximize something, then the global maximum. If I'm trying to minimize something, the global minimum. So how does one find the global minimum over, say, a closed interval? Just let's go back to what your old calculus said, that suppose that was the function up there, and this has vanished from the screen. Let me bring it back for you. It's that function, and you have a picture there, but suppose it was given analytically as an expression, and I wanted you to find the global minimum between the points -2 and +4. How would you go about doing it? Yeah?
Boundaries? Yeah.
Find all values of x where the f prime x is 0.
Yes.
And compute the second derivative.
Yes.
Find out the minimum points, then fit it back into the equation and find out this is the least value.
Will that suffice? Yes?
You don't have to check the endpoints?
Yes. So the gentleman here pointed out you have to, a little bit of a problem that we didn't, one more little story I'm just telling you that the function is continuous, not differentiable. It sometimes happens. Why do we care about these continuous functions versus not differentiable functions? Because sometimes in optimization problems, if x is less than something, you do something else. If x is greater than something, you do something else. And at that boundary point, things are not differentiable. So if you're given a function which is continuous only, not necessarily everywhere differentiable, then how would you modify this rule that was just suggested? What else do you have to check?
Check the boundaries.
So so far, if the function is differentiable, then we know we want to check the points where f prime x is equal to 0, meaning the stationary points, the boundary points, and that's all. That's all that is necessary. But if I tell you that the function is only continuous, not necessarily differentiable, then will these 2 points suffice?
Also, check the point at which the function is non-differentiable.
The point at which the function is non-differentiable. So in addition to the points at which the stationary points, the boundary points, you have to also check the points where things are not differentiable. We've not talked about that because it doesn't happen very often, but it's something that you should keep in mind. And typically this last phenomenon, checkpoints where the derivative does not exist, typically happens when, well, in operational context, what happens is that you've got two different technologies available. Below a certain operating point, you use one kind of technology. Above a certain operating point, you use a different technology. Things are continuous, but not differentiable. So that's something that one has to check. All right. Okay, so we have enough story available to try to solve our first optimization problem. And this is the problem that we're going to try to solve. And we'll try to illustrate a few things using this problem. So MM stands for Mortimer Middleman, operates a diamond business. He lives in Antwerp. Oh no, he travels to Antwerp from wherever he lives several times a year to replenish his diamond supply. The details of his business are as follows. He pays $700 per carat, the wholesale price. The retail price that he can charge is $900 per carat. The trip from his local place to Antwerp and back, costs him $2,000. It's a fixed cost, and it takes him 1 week to do this entire trip. The demand for diamonds at his place is 55 carats per week, and no back orders are allowed. What does it mean? A back order, that's just a buzzword or a lingo which says that if a person comes to buy diamonds from this Mortimer Middleman and he doesn't have diamonds available, he can't take an order and then fill that order after he goes and picks up diamonds. He loses that customer. Okay. The inventory holding cost, this involves the cost of paying the security guard, putting a nice big, renting a bank vault or whatever, is $3.50 per carat per week. And the question now is, what should he do or what can he do to maximize profit? It's an extremely word problem. I mean, think of MM coming to you with this data. This is all the data that he's got in his pocket. And he tells you, look, this is all that I have, and you tell me, what do I do? So, how would we start? Where would we start the story here?
How much diamonds you think in a single trip?
Okay, so the first thing somebody stated an objective function. The first thing that in an optimization problem that you have to start with is something called the decision variables or the decisions. And that's just words. It's just the decision that he's going to make. And typically, since we're going to be talking about some quantities, some real numbers, we'll put decision variables. Decisions stand for word description of decisions. In an optimization problem, we have to somehow translate the decisions that this person has to make into some numbers that I'm going to try to find. The best possible numbers which would optimize his profit. Okay. So what are the decision variables that Mr. Mortimer has to do?
How many diamonds he carry in one trip?
Okay, so let's call that Q. Quantity bought per trip. Anything else?
Number of trips in a particular time.
Uh,
Let's take it as 1 week or 4 weeks.
1 week is enough. Is that true? So, the lady there who suggested 1 week, can you justify your choice? Why 1 week is enough?
Because if we are looking at profit maximization and it takes up 1 week, even if we maximize for the week and we maximize for the month, we can only make 4. It's just a scalar.
But in a way,
But he did not want to make 4 trips. Who told you? I mean, the data simply said it takes him a week to make the trip. But he didn't want to make the trip only once a year. Right? I mean, one could. So, what I'm trying to point out here is that when in an optimization problem, when you're trying to restrict somebody's choices, better make sure that restricting those choices are not going to remove some profit opportunities for this person. All the time when we do, we're going to restrict choices. There's never going to be an optimization problem where we're not going to throw out something. But we try to keep as much as possible. Right? So let's just say, I don't even remember what. Let's say, let me define as R to be the interval between trips. You could define different variables. I mean, it doesn't really matter. Oh, yes, I forgot something. Our friends up there in the TV world don't like red pens. Okay. You could have defined another quantity here. You could have been, yes. Hello? Oh, that's not good. Okay. I think there should be one. But I'm trying to figure out how to put this replacement in, which is going to be a challenge. Okay. Not too bad. Okay. This is a technological issue here. Work? Does that work? Okay. So what did I do with my pens now? Okay. All right. You could have used, instead of R, we could have used, say, the number of trips per year. It doesn't really matter. And now, we have identified the decision variables. Now we want to write out, so the basic program that we are going to use in this optimization, in this particular case, and these programs change as we get more and more methods, more and more ways of doing optimization problems into our pocket. But the first thing you always do is try to figure out what are the decision variables. Then you write the function, the profit, as a function of these decision variables. And today we only know how to compute derivatives. So today we're just going to use the derivatives to try to figure out what's the best thing Mr. Mortimer Middleman could do. As we learn more techniques, we'll use some other techniques to do it. So the first 2 steps are standard. The last one depends on how much you know. The more tricks you know, the better you can do it. Okay, so using these 2 quantities, I want to write out the profit. Now here comes the tricky part. How does one write the profit function now?
200 into Q plus R into D.
200 into Q. Now why are you assuming that he could have sold everything that he bought? The demand is only 55 per week. If he buys 2,000, he cannot sell it. So you've got to somehow push the demand into your profit, right? So you can't simply say that everything that you buy is available for selling. I have to somehow put into the thing that there is this demand function there. I could say something very simply, which is say that you buy only something that's less than equal to demand. We can deal with that, then it will solve the problem. But I'm restricting his choice. So maybe that's not the best thing he wants to do. So maybe there is some other way to model the problem. So how do I figure out what is the profit function? Yes?
Just make it be the minimum 200 times Q and 200 times B.
So the minimum of Q and B times 200. Right. The thing to remember, here's another little bit of a problem. No back order allowed. So when this fellow's gone off for a week to Antwerp, things show up, demand shows up, but the door's closed. So I have to deal with that somehow. What does that depend on? That depends on R. The number of times Mortimer traipses off to Antwerp, he loses customers. And that is why this every week going off to Antwerp is a problem. But there's another thing that you guys have implicitly assumed without really thinking about it. What about this demand here? It just says, what is an implicit assumption that you've already made about the demand? When you're writing expressions like that, the profit function is 200 times the minimum of D and Q. It's constant. So that's an assumption. You should be aware of these assumptions. Given this information, there is no other assumption you can make. You might as well just assume that the thing uniformly arrives over the week. That the demand arrives at a uniform rate of 55 per week. You don't have any other information available to you to make any more refined judgment about it. But that's a problem with the data. You have to worry about it. And in the other course that you guys are going to be taking, which is stochastic processes, they're going to look at this deterministic assumption and say this is garbage. Demand is never deterministic. Most of the problems, if everything in the world was deterministic, life would be really simple. You don't have to worry about anything. Most of the problem comes because this thing is not deterministic. It varies. And when it varies, you have to hold a lot of inventory. Because just in case a lot of people show up, you want to satisfy them because they are a profit opportunity. But at the same time, you are holding a lot of inventory and nobody shows up. Then you pay a cost. But for this particular example, we're going to assume that it is going to be deterministically arriving and work with that. Okay. So given all of those assumptions, which are down here, another nice thing I can hide things. So we're going to assume that the demand is deterministic with rate D. So the decision now reduces to the reorder quantity Q and the reorder level. So I guess let's not call this interval. Let's call this the level at which MM reorders. So the story is something like this. Here's the timeline. He starts off with some quantity Q. He's just finished his trip. He shows up with the time Q. Demand starts arriving at a uniform rate. So the slope of this is D. When the demand falls up to a level R, Mortimer decides to go away to his trip. The demand still keeps arriving. After 1 week, so this period here is L. After 1 week, he shows up with a quantity, and it becomes bigger again, and then again it decays down. And those are all R's. So this is sort of the picture that we are going to think towards. And one thing to keep in mind is that this nice picture about using the reorder level only works in some sense because things are deterministic. If things were stochastic, you might have to do something more refined. But once this is done,
So how can quantity decrease in that period when he's gone out?
he's bought an assistant. What it means is that if this point happens to be 0, when it says no back order, what it means is that if your storage, if the number of diamonds that you hold are 0, then you can't serve anybody. So this picture could also look like, depending upon the time when he reorders, he could decide to reorder at 0. So what happens is that he comes here, this is R, 0. For 1 week, he cannot get anything, and then he goes back to Q. So here there are no sales, no demand. That's what back order means. There's no back order. Otherwise, what he could have done is that over this period, his shop assistant could be taking orders and saying that, look, in a week, I have got stuff available, come back and I'll give you the diamonds. So no back order means if you don't have the stuff on hand, you cannot sell it. Okay, so this is what the picture looks like. R here is the inventory rate. So if you, the first thing that we're going to do is like, what's your name back there? No, the one behind. Rupa. Like Rupa suggested, let's do everything over a cycle. Okay, 1 week is bad maybe, but this cycle gets repeated every time. So we will think what happens over this cycle is just a repetition, right? So let's maximize the profit over a cycle. And then all that happens is that the cycle gets repeated. The only thing was the Rupa suggested that let's make the cycle 1 week. Let's not make it 1 week. Let's make it long. So what is the revenue and cost per cycle? I wouldn't belabor you with all the algebra there. This one I know is correct. So you can write the expression for the inventory cost in this manner. It's just a matter of taking the area under the triangle and so on and so forth. So the first term here is the area under the triangle, the second term here, and this is a notation that we'll see often in this course. What this notation means is that you take the first compute the quantity inside the bracket. If the quantity inside the bracket is non-negative, then this bracket plus means just take that value. If the quantity inside is negative, then the plus puts it equal to 0. Okay? So you take the quantity only if it is non-negative, but if it's negative, you set it equal to 0. That's what that notation means. And when you're going to take more of these option type courses, you will see that that actually is what happens in a call option or a put option. One side you get paid, the other side you don't. Question?
Why do you assume that the reorder level is constant?
Because the demand arrives deterministically. So there is no loss of optimality by just assuming everything is constant.
But for example, if there is no inventory cost, I expect to do a lot of trips.
Yes.
One after the other.
Right. So if as soon as H is positive, if there is some non-zero inventory cost, then it doesn't really matter. Yeah, at H equal to 0, I agree with you, in which case he might as well just sit there, hire a bunch of people, and who will just keep going up, back and forth. As soon as H becomes positive, so for the moment just assume that every quantity in here, the P, the H, they're all non-negative, I mean strictly positive. Then it doesn't really matter to me whether I make it fixed or not. Even non-fixed, I can replace it by something which is fixed. Yes?
But why is he saying, I don't understand, because it still costs 2,000 each trip, so even if H is 0.
So there is a possibility that he might want to just pile up everything and keep it there. Instead of going, coming, and going, he could just go there, collect up a whole bunch of things, and put it in his shop. And never go again. Right? The only reason you won't do this is because H is not 0. Otherwise, you'll just pile up everything, right? You will never want to go back again. Okay, and that, so I mean, it's not practical, but it's something will become a manifestation if H is 0. All right, so you just compute those things. The lost sales is P times DL minus R plus. So the total quantity that he's trying to maximize is this quantity here. The algebra, you can work it out, and if you don't understand the algebra, then I can explain it to you offline. It's not very important. Okay, so what we want to do is maximize this expression over two quantities, Q and R. Those are the two decisions that I can make. I can decide how much quantity to buy per trip, and at what level should I kick in the trip. So this is a problem with two dimensions, two variables, and so far we only have learned how to do things with one variable. Another thing that has been ignored here is that I've ignored the constraint. Constraints are something that limit our choices. So far we are just saying maximize this thing without regard to what happens to Q and R. But in reality, Q and R have to be non-negative. You cannot buy negative amounts of Q, and certainly you can't have negative reorder levels. But we are ignoring them. This is a trick that's often used in optimization, that we ignore them in the hopes that the optimum value would always satisfy these constraints. If the optimum value satisfies these constraints, then we don't have to worry about it. But for now, we are just going on faith that yes, things will work out. The other thing that we have ignored is that this Q, somebody doesn't like optimization over there. No. This Q typically is discrete. You cannot buy continuous amounts of diamonds. You might have to buy them in lots. And towards the end of the course, we'll talk about integer programming, where this lot sizes becomes important. Anyhow, so let's see what we can do with this function for now. So we have two variables in this problem. If I'm trying, first let's say that we choose some level q. Okay? You fix the level q, then what is the optimum choice for r? Since r is completely unrestricted, this kicks in when r is greater than dl. That starts kicking in when r is less than dl. There's a negative sign in front. So the best thing you can do is set r equal to dl. If you don't set r equal to dl, you get a cost either from that point or from this point. And you can remove that cost by simply setting r equal to dl. Right? That's just an observation from there. Now, once you do that, then the problem that you end up getting is this. Maximize pq minus h over 2d q squared plus f. Why? This quantity drops off, that quantity drops off, and that's the remaining expression. Okay. Take the derivative. F prime of q becomes p minus hq over d. Set that equal to 0. You end up getting q star. The optimum, or the candidate optimum, is pd over h. Take the second derivative at the same point. This point is a constant. You get 0. The derivative of that is minus h over d, which is less than 0, which means that q star is the local maximum. Okay. Is this a global maximum? First of all, when we are talking about global maximum, what is the range? What is the relevant range over we are talking about here?
Greater than equal to 0.
Greater than equal to 0. Remember, there is this constraint that q must be greater than equal to 0 that we have ignored. Okay. Luckily, the q star that we got is all positive. I mean, these p, d, and h are non-negative, positive numbers. Therefore, this q star is positive. It's in the range. It does not violate the constraints. Now we want to talk about global maximum. And it is a global maximum because the function value at plus infinity is minus infinity. If you look at this function, this is a quadratic term with a negative sign which dominates over the linear term. So if q becomes plus infinity, this becomes minus infinity. So plus infinity, which is one of the boundary points, cannot be optimum. The other boundary point is 0, at which point you get a quantity minus of f, which is less than f star of q, which is p squared d over h minus f. So you get a non-negative, you get a positive contribution at q star, and therefore q star is optimum. Another reason why we could have forgotten about all of this and just looked at this expression and said, yes, q star is the global maximum, because the function f of q, which is the function up here, is a concave function. For those of you who know concave functions, it's well and good. For those of you who don't, you don't have to worry about it right now. We'll come back to it and define what concave functions are. But the thing that I want you to remember from here is simply that concave functions are nice functions to maximize. You just get a local maximum and you're done. You don't have to check anything else. If the function is not concave, then you have to go through the struggle of trying to check for all boundary points and points where their derivative doesn't exist and so on and so forth. So we will try to make things concave for maximization and convex for minimization. Here, let's not worry about it. Okay, so we have solved our first optimization problem. We computed q star to be pd over h, and we computed the optimum interval to be d times l. This sort of makes sense. D is the demand rate, L is the time that it takes. You sort of want to keep, basically what it's trying to tell you is you reorder at a level, essentially what it's saying is you reorder at a level R such that in 1 week you exactly hit 0, and then you go back and reach the level Q. That's all it's saying. So this length is L. The demand that comes is at the rate D, so R star is equal to DL. The shop never runs empty. So nothing surprising in that. Now, about this quantity Q, is that acceptable? Do you think that if you were to suggest this Q to Mortimer Middleman, he will accept this solution?
The profit per trip is not exactly the profit in a particular time period.
So
True. But what's wrong with this? It may not be the thing, but what would go wrong if I give him this solution?
say the trip is, the time difference comes too big.
Yeah.
Average profit in a particular week.
Actually, if the time is large, then the average profit becomes closer to the quantity, right? As the time becomes larger,
So yeah, right. The other way around.
yeah, the other way around is a problem. But just looking at the expression, what's the thing that's striking to you here?
Just say it has to be an integer.
Don't care right now. Let's just say it's continuous. Those are second order issues. Yes.
Is the cost the 2,000 per trip?
Yes.
Not really. What's the variable for that?
It's not there.
Exactly. So
So
pretty relevant.
that's pretty relevant. So clearly Mortimer is not going to accept this solution. Because if you look at this, if you stare at this solution and you look at it and it says, well, if the cost per trip was 0, you still order that much. If the cost per trip was 2 million, you still order that much. The quantity that you order does not depend on how much the trip costs. That doesn't make sense. It cannot possibly be right. If the trip is expensive, you're going to try to order more. You don't want to make too many trips. So what went wrong in the modeling?
The profit may be negative.
Profit may be negative, yes, but that's a consequence of the model.
We modeled for per trip wherein we should have.
We didn't model, yeah, we modeled per trip,
Yeah.
whereas what we should have done?
We should have modeled for per week or per fixed time period.
Multiple trips.
Some fixed time period.
Good. So how do we fix this problem? So we go back and put down, and this my page down thing is rather, so that's exactly what the suggestion is, that you cannot do it over a cycle. Whether you go every week or not, but essentially what happened was that in every trip you made in every cycle you made one trip. So your time was renormalized as the number of cycles that did not account for the fact that there is some normalization over time that goes off in the trip cost. So now you get a little bit more complicated expression where this capital L is now the length of this time period. We were not averaging over the time period. One thing could be done, you either take a week, or what you do is that you take this interval, capital L, and you take the profit and divide it by L and maximize that. Okay? But the thing to remember is that this quantity L is itself a function of Q and R. The length of a cycle depends on how much you order and when you order. So this is what the expression you get. It's a bit trickier, but you can again show that the best thing to do is put R star equal to DL. Sort of makes sense. You don't want to lose anybody, and so you put R star equal to DL. Now if you put R star equal to DL and simplify things, you'll end up getting this optimization problem. PD is a constant. Here you get minus HQ over 2. Here you get minus FD over Q. You solve this for local maximum, and now you end up getting that Q star is equal to plus or minus square root of df over h. And you get that from looking at the first order conditions. And at the positive value of Q star, you end up getting that the double derivative is negative. So one has to answer the same question. What about the negative solution? What do we do with that? It's not feasible. We really had to have the constraint Q not equal to 0. So at this point, we're going to look at the negative solution and claim that that's not in our domain. Throw it out. So then comes the question, why could we ignore Q greater than equal to 0? We could ignore Q greater than equal to 0 simply because for every value of df and h, I know that Q star would be strictly positive, and therefore it will never be at 0. So I could have ignored that. Now, does this solution make sense? Q star equal to, so meaning that this time around we got our Q star to be equal to 2df over h. So this is independent of P, the profit, or the profit rate. Is that okay? So this time we got back the F. We got the trip cost. So if the trip costs more, then you'll order more. Makes sense. If your inventory costs are less, you're going to order more. That also makes sense. And in the limit, if the inventory cost is 0, then Q star would be infinity. You just order once and never order again. Now, the thing that's missing out here is P, the profit rate. Is this okay that the solution doesn't depend on the profit rate? No matter whether so right now his P is equal to 200 per carat. What if this was changed to 400 per carat? Should that change things? Should that change Q star? This formulation says no. But is that acceptable? I mean,
Demand should be the function of price.
no, demand is fixed, let's say. He just charged more.
So because your revenue is kind of fixed, so I mean it's really that you're minimizing costs.
Yes, if you set R star equal to DL, I agree. If you set R star equal to DL, then you're trying to minimize cost.
So I mean from that point of view,
So it may be possible that if the profit becomes a whole lot, you might always keep an inventory. Does that make sense? I mean, I'm just trying to be a devil's advocate here. I'm just trying to look at this solution and I'm trying to say, well, if I were Mortimer and said, well, you don't have P in there, I don't accept your solution, what would you answer? Last time if I had objected this and said you don't have F in there, then there's a problem. I mean, that you have to correct. Here if I tell you that if P is not there in your expression, would you try to convince me that no, P shouldn't be there? Or would you go back and say, well, okay, let me change my model? What would be, I mean, those are the two possibilities, right? When F wasn't there, we scrapped that model and said, well, we need F. We went and put a different model. Now we don't have P. What is it? Yes?
Well, in the example, we care about cost, only cost. We don't care about the profit. I mean, if we sell something, the profit will come at the end.
Yes.
So we don't have to worry about it. We
Yes.
just have to worry about the cost. So it is normal not to have the profit in the solution.
Okay. So your statement would be that Mortimer should accept this solution, and there is nothing better he can do.
Probably something better, right?
No. I mean, with our limited knowledge, this is the best we can do. And the reasons you're giving is absolutely right. The only thing, effectively by setting R star equal to DL, the only thing, we have captured all the demand that can come into our store. The only thing we are doing really is try to minimize costs. And when you're trying to minimize cost, then P shouldn't play a role here. Yeah.
But it's because our demand is constant.
Yes.
That's exactly why.
Yes.
Right? If it wasn't constant, then the profit would have a huge impact because the risk of losing that profit would be huge to us.
Well, that's actually depends. Well, the objection that you're raising is at two levels. So we could do the entire analysis that we did. Let's say the demand was not constant. Let's say the demand was variable. But we did the entire analysis for the expected value of the profit. You'll end up getting the same answer. So the question, what you're saying is that if Mortimer is not only interested in the expected value but also variability, and most businesses do, most businesses would like to give up some on profit in order to get a fixed or a somewhat fixed cash stream all the way through. And if that happens, then you're absolutely right that P will play a role. But if you're only interested in maximizing the expected profit, you don't care about variability, then nothing will change. The story will be the same. But typically people don't. People will be willing to give up some on optimality to get less variable solution. You don't want to, you don't want to go and keep contracting for more space, less space, more space, and less space. That's just not a done thing. Okay?
We are also assuming that he's got enough margin per carat to offset all his costs. Because
so in this particular thing, if you go and put in the expressions, it'll turn out to be right.
yeah, but say my P is 0, I would still be
Yes.
ordering something which is meaningless.
P is negative, it becomes a problem because you still break even or something. Yeah, yes, actually, that's true. You're trying to just minimize cost here. You're right. All right, any questions of one-dimensional minimization? This is the only time we're going to talk about one-dimensional derivatives and minimization. So any questions about this stuff? I'm going to assume that you remember, recall, are conversant with, completely happy with one-dimensional minimization. So, yes?
I just didn't understand one thing, how you got that equation to begin with, a large equation. It's just that's the standard way it's formulated. I mean, write an equation.
For the picture, you mean?
No, not the picture. The
Yeah.
equation, when the maximum.
Which one?
Even before you had this, before the 1 over, no, it's the same thing though, but it just didn't have the 1 over L.
Yeah.
You just said that was the equation. That's just, I've never seen it before like that, so.
How do you get this?
Yeah.
Okay, so
Well,
here...
you put all the variables together, right? And
I don't get it. Your question is, how do I get this expression?
it's basically related to the word problem. And
Yes. So the only thing I did was I looked at this picture and I said, well,
area. Okay.
so this area is the inventory cost, which is this quantity here. So if R is greater than DL, so let me just quickly tell you what this is and we'll go on. So here's Q, here's say R. So if R is greater than DL, what happens is that the inventory never goes to 0. So this quantity actually let's not say what level this is. So this level here is R minus DL, the total demand that you see over the 1 week period. This is L. At this point, he orders an amount Q, so this point here becomes Q plus R minus DL. And the total inventory cost that I have to compute is over this area, this trapezoidal area. If R is, and therefore what I'm doing basically is taking the height of this equation times times this, that and that divided by this. That's basically what I'm doing. The only issue is that if R is less than DL, then I don't pay inventory cost over this negative interval. So I have to handle those two different cases. And one way to handling different cases is by using this expression of R minus DL positive part. That immediately takes care of what happens when R is greater than DL and what happens when R is less than DL. Okay? And I'll probably leave it to Ali to go over it in more detail in the recitation if they wanted to. Okay? Any conceptual problems that you have about derivatives and so on and so forth? Ali will go over some example derivatives as well to make sure that you recall all the rules for taking derivatives and so on. Okay. So next topic that we will cover will that be of taking this whole story up to multivariable. So now instead of having a function that goes from a real line to a real line, we'll have a function that goes from a vector, takes a vector and maps it to. So now I'm talking about functions that go from Rn, meaning an n-dimensional vector, to R. So it takes a vector and puts a real number. And again, the story that we are trying to find out is, the basic problem that we're dealing with today is how do we find a point x0 which is a local minimum. So again, the question that I'm after is that I've given now a vector x0 and I want to figure out, is f of x0 less than equal to f of x for every x, or this inverted A stands for every, for every x, such that its length, if the difference of x minus x0 is less than equal to delta 0. It's the same story as it happened in one-dimensional problem. In the one-dimensional problem, we were looking at the point x0 and we were saying, if I perturb this guy around the point x0 somewhat, a small amount, I want to make sure that f of x0 is the smallest possible in that interval. Now, instead of talking about moving in one particular direction, what we are saying is that if the length, the distance of x to the point x0 is small enough, then f of x0 must be smaller than or equal to f of x. All right? And again, in order to answer this question, what we really want to do is get a Taylor series expansion. We want to get a Taylor series expansion of the function f of x at the point x0, the generalization of the idea of one-dimensional problems. So what the Taylor series expansion says is the following. That f at the point x plus some vector delta. So x is a vector, delta is a vector now, can be written approximately as the function value at the point x0 plus summation of I going from 1 through n. Remember, the function goes from Rn to R, so it's a function from n-dimensional vectors to the real line. Take the partial derivative of the function with respect to each of the components xi and multiply that to delta I. So let's take an example. Let's take f2 of x, and let's put some numbers to these sigma 1, sigma 2. Let's say it's 2x1 squared minus 6x1 x2 plus 9x2 squared. Let's say that's the function. So what is the partial derivative of f with respect to x1? So when you compute the partial derivative, you pretend as if x2 is a constant. You don't even think of x2 as a variable, just think of x2 as just a constant. So the first one here gives you 4x1 squared. Oh no, sorry, 4x1. The second one, x2 is a constant, so you end up getting 6x2. All right? And similarly, when you take the derivative with respect to the other component, you assume that the first component is a constant, so this becomes 0 because this is a constant. From here you get minus 6x1. From here you get 18x2. So the definition of a partial derivative is that you take the derivative with respect to the quantity that you are interested in, pretending that everything else is a constant. So the Taylor series, the first order Taylor series expansion, says that f of x0 plus delta is equal to f of x0 plus the partial derivative times the perturbation. So just recall what happened in the one-dimensional case. In the one-dimensional case, we had only one variable. So we had f of x plus the derivative with respect to that one variable times the perturbation. So in the one-dimensional case, there is no partial derivatives because there is only one variable. This is simply a generalization of the same idea that you have here. Here you have multiple variables, so you have to take a derivative with respect to all of those variables. In the first case, you had just one variable, you just took the derivative with respect to that variable. Okay. A more convenient way of writing this is if you think about this summation for a moment, it starts to look like an inner product. It's an inner product of two vectors, where the one vector is this delta vector, the perturbation vector, and the other vector is a vector of partial derivatives. So you can write this as f of x0 plus this vector, where the first component is partial derivative with respect to x1, x2, xn, transpose times this vector delta, which is delta 1, delta 2, delta n. It's exactly the same expression. You just took, it's just an algebraic manipulation. So this quantity here, this vector of partial derivatives, is called the gradient vector. So it's a notion, it's just a generalization of the notion of the first derivative. Instead of talking about just one derivative, we talk about a number of derivatives because there are a number of variables. So this quantity I'm going to write as f of x0 plus the gradient, which is usually written with this inverted triangle, or whichever way you want to think about this, inverted or not inverted, at the point x0 transpose delta. Okay? It's just this vector has a notation gradient of f at x0. All right? Okay. So let's go back to this story. F of x0 must be less than f of x for all small enough distances, for all x that are at a small enough distance. So what does this expression tell me about the gradient vector? 0. The gradient vector must be a 0 vector. Why? Because all possible perturbations deltas are allowed. So if it has something non-zero, and if f is less than f of x in one direction, then if I flip the direction delta, you'll get something larger. And therefore, we'll end up getting that this implies that the gradient of f at the point x0 must be equal to the 0 vector. Every component must be 0. Okay? Simple generalization. All right? Now let's go to the next step. So after the first order Taylor series expansion, let's move over to the second. Let's see whether I have it here. Okay, here we go. The second one wants to get a generalization of the story that we had for one-dimensional cases. So in the one-dimensional case, the Taylor series expansion said that f of x plus delta, this is not vectors, this is just one-dimensional, is if f of x0 plus the derivative with respect to the first component times delta plus 1/2 times the derivative with respect to the first component of the derivative with respect to the first component times delta squared. Right? This is what our Taylor series expansion was. This double derivative I had written as f double prime, but I'm just using the definition. So here the generalization would be put a half, but now I'm going to take a sum over I going from 1 through n, sum of j going from 1 through n, take the second derivative, or second partial derivative of f with respect to xi and with respect to xj. Multiply them by the perturbation in I and the perturbation in j. That's exactly the analogous statement for the one-dimensional case, except that you have now multiple variables. Here you just had one variable to work with, so you took two derivatives with respect to the same variable. Here you've got multiple variables, so you take pairs of them. All right? Again, we're going to try to simplify this. So we can write this whole contraption here, this as this matrix vector product. Take the vector delta, take its transpose, and construct a new matrix whose components are the second partial derivatives. So the first component is with respect to x1, the next one here would be x1, x2, and so on. And in general, it will be del squared f over del xi del xj. This is the sort of the general component here. And then you hit it with another delta on the other side. So this quantity here, this matrix vector product, is exactly equal to that quantity up there. Just work out the algebra and you will see that it's exactly this summation. This messy looking quantity in here, this matrix, is called the Hessian. So let's compute it for this expression over there. Let's choose a point, doesn't really matter. Let's take the point x0 to be the point 1, 1. So at that point, the gradient vector is given by -2. I just put in the expression here, and over here it's 12. Now when I compute the Hessian, I need to take the partial derivative of this guy again. So you get the partial derivative with respect to x1 squared to be equal to 4 from here, and this is a constant, you get 0. Del squared f del of x1 and x2 turns out to be, from here you get minus 6, there you get 0, and then I need one more quantity which is x2 squared, from which I get 18. So the Hessian matrix in this case does not depend on the point, and it's given by 4, minus 6, and 18. Right, so this, let me just put a, so that's the numerical kind of calculation that you'll have to end up doing for second order Taylor series expansion. So writing this a little bit more concisely, for two-dimensional cases, what you end up getting is this, which says f of x0 plus the gradient of f at the point x0 transpose delta plus 1/2 of the vector delta transpose the Hessian h at the point x0 times delta. And h is this, for this particular example, that's the expression. And so for that example, at the point x0, the Taylor series expansion would look like this. What is the, I don't know what f of x0 is, plus the gradient vector is minus 2 and 12, transpose delta 1, delta 2, plus 1/2 of delta 1, delta 2, times the Hessian, which is 4 minus 6, and 18, times delta 1, delta 2. What? Ah, this one is transposed, yes. So that's the Taylor series expansion. Okay, so let's ask the same story here. The first order Taylor series expansion tells me that if x0 is a candidate for a local minimum, then this is gone. So we're left with f of x. So f of x plus delta is approximately equal to f of x0 plus this quantity, which is completely the same as we got for the first order case. Now, what do we need this guy to do in order to make sure that x0 is a local minimum? So non-negative definite. So let's not, so that is, does everybody understand positive semi-definite or non-negative definite, these terms? No. Okay. So ideally what we want to do is the following. We want to do the same thing that we did for the one-dimensional case. So let me just remove this. So what we want to ensure is that no matter which delta I pick, this quantity better be non-negative. That's what we want. So in order for x0 to be minimum, in the one-dimensional case, what did we do? In the one-dimensional case, we had this. And we said, well, we want to make sure that no matter which delta I pick, this quantity has to be non-negative. That would make sure that f of x0 plus delta is greater than or equal to f of x0. We want to do the same thing down here. We want to make sure that f of x0 plus delta is greater than or equal to f of x0 no matter what delta I pick. So what I want is that this quantity, delta transpose h of x0 delta, must be greater than or equal to 0 for every delta in Rn. No matter which delta I pick, I need to make sure that that product, whatever that is, has to be non-negative. This means, this is the same thing as saying that the matrix H of x0 is positive semi-definite. This is the definition. The semi part comes from the fact that it can take the value 0. If you wanted this to be strictly positive, then you would have called this H of x0 is positive definite. But right now we will work with positive semi-definite. So how the hell are you supposed to check that this thing is positive semi-definite? A lot of different ways. For as far as this class is concerned, you go to MATLAB and you hit a command called eig. You take compute the eig. This will compute a quantity called the eigenvalues. You may or may not I think in this class for sure you would not need to actually know what eigenvalues are, but I'm sure. But I'm sure that when you go into stochastics, we're going to talk about eigenvalues, particularly various kinds of equilibration and things of that sort. But for us, we'll just say you go to MATLAB and compute. You give this command. This will compute the eigenvalues, and you check whether the eigenvalues are non-negative. If they are non-negative, h of x0 is positive semi-definite, which means that this is non-negative. All right? It is just a generalization of the idea that we had here. We wanted the second derivative to be non-negative. Now we can't talk about one second derivative. There's a whole matrix sitting there, this entire matrix. So what does it mean to be non-negative? It means that no matter which delta I hit it with, this quantity is non-negative, which is the same thing as saying if I compute its eigenvalues, which this command computes for us, then that's non-negative. If you want to understand more about eigenvalues, I'll be happy to tell you offline. I don't think we'll have the time to cover that in class. All right. Okay, but now we are stuck with, so let's say we know how to check whether something is positive semi-definite. We're still stuck with the same old problem. This implies that h of x0 is positive semi-definite. But it doesn't imply the other way. Yes?
It's not possible.
Which one?
The last
Oh, you can't see it? Okay. What's the height that can be seen?
Yeah, here. Yeah. Yes.
Okay. So the implication goes the other direction now. So one way to correct is to make the implication go upwards and not downwards. All right. So this implies that the Hessian matrix is positive semi-definite. But it does not imply the other way. Same story as before. Whenever you sort of are a bit confused about multi-dimension, think about one dimension. In one dimension, we had said that the second derivative must be greater than or equal to 0. So the fact that something is local min implies that, but the fact that it is greater than or equal to 0 does not imply that it's a local min. For example, if it is 0, it doesn't imply that it's a local min. Same story here. So how does one go further in multiple dimensions? What is the notion of a third derivative? If the second derivative fails to give me the information, I need to go to the third derivative, like what happened with the one-dimensional case. In the one-dimensional case, I said, well, second derivative is 0, doesn't give me information. I have to keep going. What's the notion of a third derivative?
Jacobian?
Well, Jacobian is actually the derivative of a multidimensional function.
Wronskian?
What?
Wronskian?
Yeah, well, you can define various kinds of things, but typically, if this doesn't work in multidimension, you just give up. There's no point in, look, a matrix here is already, if you're talking about, say, a 10-dimensional problem, you're talking about a 100-dimensional quantity, a 10 by 10. A third derivative will be 1,000 by 1,000. You have to get, sorry, not 1,000 by 1,000. It's a cube, 10 by 10 by 10. So it's going to be a 1,000-dimensional quantity. You can work with it, and particularly mechanical engineers seem to work with those kinds of things. And there are material properties that are changing here and there. But us, we just say, okay, we give up. We'll try to get at it from a completely different way. And so in terms of multi-dimensions, we only worry about the second derivative. If the second derivative doesn't give us complete information, then we'll design other techniques to deal with it. So let me close this lecture now with an example of a multi-dimensional optimization problem. The most popular one, perhaps the sort of canonical example for very simple multidimensional problem is something called the least squares problem. Least squares problems will show up, at least in applications, they show up in fitting parameters. You describe something by a model, you've got data, now you want to calibrate this model to the data, and you want to choose parameter which gives you the best fit. That's a story of parameter fitting. If you want to fit data by taking something called the squared error, you take the error between the model and the data, take that difference, square it, and add them up, and now you want to minimize this error, then what you get is the least squares problem. The least stands for the fact that you're trying to minimize something. Square stands for the fact that it's an error that has been computed by taking squares. So here's an example. The T-bill rates for 1998 are this quantity. This is all given in a per annum basis, 4.28%. I was just thinking about it yesterday. It almost looks that the rates are going back to the same level. It's like, what is it now? Does anybody know?
3.25.
3.25. So, okay. So another 6 months, it will probably be 3.5. 4. All right. So anyhow, it's trudging back to the same level. So if any of you hasn't bought a house already, you probably should. No. All right. So let's say we want to model this thing by something called an autoregressive model. Why is it called second order? It should have said third order there. Okay. This should have been a third order autoregressive model. So what is an autoregressive model? It says that the future rate can be predicted by looking at what happened in the past. There is a trend, and I'm going to use the past interest rates to predict what happens in the next interval or the next period. It is erroneously written second order. It's a third order model because you use past 3 data points to predict the next one. And what's this epsilon? This is some error. This is the error that we are trying to minimize. So we are trying to figure out what A1, A2, and A3 should I choose in order to minimize the error of this model with respect to the data that I have. This is the data that I have. I want to use this data to compute A1, A2, A3. And since I have 3 different components, I'll end up getting a multidimensional problem because my error will be a function of 3 quantities. So a very popular method is to minimize the squared error. And what is an error? You look at what the data what your model predicted, and compare it with what the data was. So you have RT is the data that you saw at time unit t. Your model said that that interest rate should have been, just forget the negative sign here, A1 times RT minus 1 plus A2 times RT minus 2 plus A3 times RT minus 3, which is the same thing as this row vector times the column vector A. Take the difference between that data and this prediction and square it. That's the error. So for t equal to 4, if I bring down the picture, so t is going this way. This is t equal to 1, 2, 3, and 4. The real quantity is 4.07. I'm going to predict it using the past 3 data points, which is 3.85, 4.14, and 4.28. 3.85, 4.14, and 4.28. And hit that vector with my prediction weights A, which is A1, A2, A3. All right? That's my prediction. That's the error I squared. Now, here comes the power of using vectors and matrices. The total squared error, I simply take all those errors and add them up. Since the first component that I can predict is t equal to 4, I'm just taking the sum from 4 equal to n, 4 to n, whatever is n. All right. If you write it out, what's happening here is that you're writing this quantity. You're writing R4 minus R3, R2, R1 times A, this component squared, R5 minus R4, R3, R2 times the vector A squared, and so on. This is nothing but the length of a vector whose first component is this quantity, the second component is that quantity, the third component is the next one, and so on. I'm using the fact that the norm of x squared is nothing but x1 squared plus x2 squared plus x3 squared plus xn squared. So out here, I've got an expression which looks like this summation. Something squared plus something squared plus something squared, and so on. And I'm going to interpret that as if it is the norm of some vector squared. And what is that vector? It's this quantity. Little r vector is R4 up through Rn. A is, of course, A1, A2, A3. And you get a matrix R that comes from just taking these rows and stacking them all up. So the first row will be R3, R2, R1. The next one will be R4, R3, R2, and so on. So now what we want to do is the following. We've got E squared, which is the norm of little r minus R A squared. And now I'm going to use the rule which says that this squared is nothing but this quantity transposed times the same vector. Use the rules of transposition. This will give you that this vector transpose is R transpose minus A transpose R transpose. And let me just make a note for my trusty TA over there, Ali. You might want to just go over this transposition rules. R minus RA. Multiply it all out, you'll end up getting R transpose times R, this quantity times that, minus R transpose times RA, which is this quantity times that, minus this A transpose R is nothing but R transpose RA, plus A transpose R transpose RA. So expression, this becomes R transpose R minus 2 times R transpose RA plus A transpose R transpose RA. A lot of exercise in algebra, but nothing very deep. That's what this expression says. This is the quantity that I'm trying to minimize. I can expand that quantity into this. If I take the first order derivatives, then you'll end up getting this expression. Minus 2 R transpose R, this is the coefficient of the vector A. So basically, when you're trying to do, just remember what happens to one dimension. If f of x was alpha times x plus beta times x squared, what you end up getting is that the derivative of x is alpha, the coefficient of x, plus 2 times beta x. So that's the same rule that's happening here. The coefficient of A here is minus 2 times R transpose R, which is what you end up getting here. The coefficient, the quantity here is R transpose R, which comes up as the same. You multiply that by 2 and hit it with the vector A on the other side. The same rule as in one dimension. And just make sure that all the matrices multiply correctly. That's all. I mean, the rule of thumb is just use one dimension and then fit it in so that things are all of the right sizes. So you get an equation here, R transpose A, you take this onto the other side and you end up getting that A star, the candidate A, is R transpose R, this matrix, inverse times this vector, which is R transpose times R. Again, as far as I'm concerned, I don't need you to know how to compute inverses. I need you to know what an inverse means. So computing part, we'll just give it to a solver to compute it. What I need you to know is what is the meaning of an inverse? It's simply a solution to this equation. If you take the second order condition, take the derivative, the second derivative, again use the same rule here. If you take the second derivative, what happens? This is a constant, drops off. This becomes 2 times beta. So the second derivative of that function is just 2 times R transpose R. And I have to make sure that delta transpose the second derivative times delta, which is this quantity, has to be non-negative. But this quantity can be written as, there's a 2 missing here, R delta squared, which is always positive semi-definite. Therefore, this is definitely a local minimum. Is it going to be a global minimum? Well, in this particular case, we will have to basically use the fact that this is a convex function, which you don't know right now. So we'll just satisfy ourselves by saying it's a local minimum. And when you solve this problem, you can either use MATLAB or you can use Excel. In the course, we will basically be supporting Excel. I myself code on MATLAB, so if you've got problems with your MATLAB coding, you can send me an email and I will figure out what to do. I think we're out of time, right? All right. So Ali will cover how to use the solver, and we'll cover it again in class. Thank you.
keeping or you?